warned, 3.9. This is a hard one. For all students at all times, this is hard because this is all going to be story problems. So like we have to think about what's going on. It'll entail drawing pictures. It'll recall remembering geometric relationships. Yup.
No limit. Like,
no limits.
Okay, I'm fine.
So this will be on the next test, but not on Tuesday's test.
I was about to say.
So the problem-solving technique that's suggested by your textbook is to start step 1, read the problem carefully. Draw a diagram if possible. Introduce notation. Assign symbols to all quantities that are functions of time. Express the given information and required rate in terms of derivatives. Write an equation that relates the various quantities of the problem. If necessary, use geometry of the situation to eliminate one of the variables by substitution. Use the chain rule to differentiate both sides of the equation with respect to time, and then substitute the given information into the resulting equation and solve for the unknown rate. So this is the kind of framework that your textbook suggests as a way to kind of work through these problems, as suggestions of things to try to do. I will kind of do all of this stuff intuitively. I don't know that this is something you need to memorize or whatever. It's just kind of a suggestion of how to begin or how to work through one of these problems. So there's no new theoretical concepts involved in this section. We're just going to be using the calculus we know to this point. No new rules, no new theorems. It's just going to be all things that we've already seen. So let's begin with our examples. I'm just going to work through some examples here. We'll start with the easy ones, and we'll get progressively more difficult as we go. So our first example says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So our first step said to read this carefully. Did you guys understand what's going on from the context of the problem? Okay. So describe to me what's taking place in this problem. A balloon is expanding, right? And what are we looking for?
How fast
The rate at which the radius is expanding as the volume is increasing, right? Okay. I don't know that we necessarily need to draw a picture for this. It's a pretty simple situation. Let's introduce some notation here. So we're told that the volume is increasing at a rate of 100 centimeters or cubic centimeters per second. What symbol should we give that? What symbol should we use to represent the volume increasing at a rate of 100 cubic centimeters per second? What? Nope.
R?
Nope.
N? A?
Nope. Nope. Nope.
Y?
It's a rate with respect to time, right?
Distance? Distance?
That's the change in volume over the change in time, right? That's the derivative of volume with respect to time. That's dv dt,
Okay.
right? Anytime you read one of these problems and something is listed as a rate, the notation you should give it is a derivative. Everybody's okay? Then it asks, how fast is the radius of the balloon increasing? What should we, that's the quantity we're looking for. What should we call that quantity? D what? Yeah, I'd call it dr dt. Right, that's the rate in which the radius is changing with respect to time. And then the diameter is 50. So we might say d is equal to 50 centimeters, or the radius is 25 centimeters, right? Okay. What equation relates volume and radius for a sphere? What's the equation? Oh. Excellent. Good job, Talika. 4/3 pi r cubed.
We're going to have to remember all these.
Probably a good idea.
So you won't give us them?
Well, it's not worrying about what I'll do. We have to worry about what the AP will do.
Well, like hypothetically.
I think in my experience, it seems like the volume stuff they tend to give you. The area stuff, probably not.
Would that be the same in the test?
Sure. All right. It says then to, okay, we've introduced some notation. We've expressed information in terms of derivatives. We've written the equation. Now we need to use the chain rule to take the derivative of both sides of this equation. So when I take the derivative of volume with respect to time, and then we'll take the derivative of 4/3 pi r cubed with respect to time. What do I get when I do ddt of v? dv dt times 1, right? But I won't bother with the times 1. Where's the 1 coming from? Just the derivative of v, right? That's 1. And because it's not with respect to v, it generates the dv dt part, right? Now, how do I do the derivative of 4/3 pi r cubed?
4/3 times
4/3 pi, and the derivative of r cubed is
3r squared.
3r squared.
Oh, dr dt.
dr dt. So that's our equation that we have. Let's look at what we have. Okay. We are looking for dr dt. That's in our equation. We have dv dt. And we have r. So we have everything we need, right? We can just plug in to solve. And now it's algebra, right? And let's do this, right?
They canceled out.
That's its radius.
And that would be centimeters, per second. Well, I reduced the 104, so that becomes 25 on top, and then one of the 25s cancels with one of the 25s on bottom, right? So that's, get ready for it, guys. That's like the easiest version of that kind of problem.
Oh, okay.
Okay. Let's look at the next example. A ladder 10 foot long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Here, I think a picture would be helpful, right? So let's try to do this without making like a degree in art be necessary. So there's our wall and our ground and our ladder. Everybody feel okay with that? Now we can assume that the ground meets the wall at a 90-degree angle. I think that's fair to assume. Most people aren't building any kind of structure so that they don't meet at right angles. Yeah, I mean, that wasn't on purpose, though.
Yeah.
It was a bad foundation. Let's now introduce a little bit of notation here. So I'm going to call this side X because it's a horizontal. And as this ladder slides away from the wall, what is that going to be called? The rate in which the bottom of the ladder is moving away from the base of the wall. dx dt. Excellent. This side we're going to name y because it's up and down. And we know that the ladder is moving down that direction. So we're going to call that motion dy dt. And I didn't give myself enough space. I'm going to just move him over a little bit. Okay. Let's name this side r for radius or whatever, hypotenuse. Now, what do we know about this? It equals 10, and it's a constant, right? Because the length of the ladder is not changing ever with time. The length of the ladder is the length of the ladder. Everybody's okay with that? Not a variable. That's the key, right? Okay. It says we're sliding away from the wall at 6 feet or 1 foot per second. And since if we assume that this is like on an XY axis and this is the point 0, 0, that should be a positive change, right? If we embed this into an XY axis, the X is moving that direction. That's a positive change in X. Everybody agree? What would we say about our change in Y? Should be negative, right? We'll keep that in mind. And this is just like building intuition, right? Because I think that's what it's asking us for, right? Yeah. That's what we're asking. And it says when the ladder is 6 feet from the wall. So this is okay. What equation can we write that relates the information going on in this problem? Yes, good. The Pythagorean theorem, right? X squared plus y squared equals r squared. Now, if we try to take the derivative of both sides with respect to time, what's the derivative of the left-hand side?
2x plus 2y.
Close. Close. Yeah, you need a dx dt and a dy dt.
Oh, okay.
Everybody's okay with that? What's the derivative of the right-hand side? Nope. Say it loud, Braden. Yeah. R is a constant,
Oh.
so its derivative is 0. That's why I made a big deal of writing constant by the R, so that when we get to this point. All right, so let's look at what we have here. We have x. We have dx dt. We're trying to solve for dy dt, but we don't have y yet to plug in.
Oh, wait, no.
How could we find y? Yes! The Pythagorean theorem, right? We know that x is 6, and we know r is always 10. Thank you. And now we have everything we need, right? So let's plug in. 2 times 6 times 1 plus 2 times 8 times dy dt equals 0.
What did she say?
So dy dt is going to equal negative 12 over 16. Which is great because we expected it to be negative, right? Or negative 3/4 foot per second. Is everybody okay here? Only slightly more difficult than the previous problem. What made this one slightly more difficult? Well, and we had to find y, right? There's one piece of information we had to get for ourselves that wasn't just given to us in the setup for the problem, right? All right. Let's put on our big boy pants for this next one. A water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Who needs a picture for this one, right? This is. So what do we mean by an inverted circular cone? We mean an ice cream cone, right? Because that's not the technical term for it. And they want to make it harder for you. So there's your water coming in, right? All right. And I did the same dumb thing I did last time where I put it right at the edge of my paper like I don't need any more space to write anywhere. Okay. Let's start filling some things in now, right? So there's our picture. And actually, let's do I'm going to do that. Okay. It says the base radius for the cone is 2 meters. So that distance there is 2 meters. I'm going to call that R subscript C for the radius for the cone, because we're also going to have a radius at the water level, right? So I want to make sure I'm differentiating that. Now, this radius of the cone is a constant, as opposed to the radius at the water level, which is going to be changing with time, right? That'll be a variable. We're told the height of our container is 4 meters. And again, that's a constant.
What is this?
Cone.
Oh.
You could call it tank, I guess. You could give it a subscript T or something. I just wanted to be able to differentiate it because we're going to have a radius for the water and a height for the water also. So it's going to be really important that I have a way to keep those apart, right? So then it says water is being pumped into the tank at a rate of 2 cubic meters per minute. What are we going to call that? It's going to be dV dt because it's a volume, cubic meters, right? Water is measured in volumes. Everybody's good there? Okay. And then it says find the height or find the rate in which the water level is rising when the water is 3 meters deep.
Oh wait, isn't it 2 meters, right?
Oh, thank you. Yep, I just wrote down the wrong thing. Thank you. So I'm going to call this H sub W. We don't know how, 3 meters. Right? And we're looking for that, right? And let's go ahead and designate this. We don't know what the radius of the water is, but that also changes with time. We don't know what that change is going to be either, right? Does everybody feel okay with what we've drawn and how we've labeled this picture? Again, drawing the picture is hard, right? That's not trivial what we just did. I've done hundreds of these problems, so I know exactly what to draw and what I need to include or not include on it. That's not always obvious. All right. What is the equation that relates these quantities together? Braden? The volume of a cone. Great. Yes. Good pull. Everybody's good here? Okay. Now, I'm going to do that. And I'm going to add W's to each of these. Probably should have put a W up here on the volume because that's the volume of the water, not volume for the cone. Everybody's good with that? Okay. So if I do the derivative of both sides on the left-hand side, I get, which is fine because we know that. If I do the derivative of the left-hand side, how do I do that? Yes, I need to do a product rule there because both RW and HW are variables. Everybody's okay? Who's starting to get a bad feeling about this?
I mean, it's not a bad feeling.
I have a bad feeling about this.
Don't think of myself. Wait, is HW constantly? Can you imagine?
What?
Or just,
No, not until we take the derivative, and then we can plug the 3 in for HW.
oh,
Because that's at a specific time, right? That's at some time t.
right.
So here's why I think we're in trouble right now. Is because we don't know RW, we don't know DRW dt, and we have no way to get DRW dt. Well, if it's not given to us in the problem, how are we going to, we need another equation that involves just the radius that we can solve, like a drw dt, which we don't have a way to create. So what I want to do is I want to look for another equation that's going to relate the radius and the height so that I can eliminate the variable rw from the equation up here. Because I don't like where this is heading because I'm going to get stuff I can't solve for. So let's go and look at our picture here. Does anybody see an equation that will relate radius and height that doesn't involve volume? A triangle. What? A right triangle, in fact. Great. So let's draw in the triangle that I hope that you're thinking of.
That is what I was thinking of.
What do you see when you look at this? So let's label some pieces. Think back to geometry.
Oh. This one was.
What is that I just wrote? Not congruent, similar. Right? Triangle ABC is similar to triangle DEC because all of their interior angles are congruent. Right? C is shared. And then clearly AB and DE are parallel lines. So angle A and angle D are the same, and angle B and angle E have to be the same. Everybody agree with that? Okay. What can I say about similar triangles? The ratio of side lengths is proportional. So I can say, for example, that AB over AC has to equal DE over DC. Everybody agree with that? Or in other words, let's see, RC over HC equals RW over HW. And why is that good? Because HC and RC, we know those are constants. Hi, Mr. Whalen.
Hello.
What can I do for you, sir?
So I'm going to chat with Jacob for like 38 and a half seconds.
Sure, I'm timing you, though.
No, not tell him. Wait. Oh. Who cares about it?
Oh, I just assumed that I would have assumed that Jacob also, given the day of the week we're talking.
Oh, what's going on today? Anything? Oh.
You guys have a game today? I forgot, too. Everybody okay there? This is what I need. Because now I can change this equation to include just HW, which is wonderful because it eliminates now R and dr dt, which we didn't know either one of those two things. Yes. Yes, I'm sorry, so sorry. Yes, yes. Thank you. We'll do that. Now just a messy W. So far, so good? Okay. Let's, if we simplify this stuff up a little bit, I'm going to end up with, I'm just going to write that as pi over 12 HW cubed. 1/2 squared is 1/4
Oh,
times 1/3 is 1/12.
oh, yeah. I just did.
So far, so good?
Wait, what did you do with this? The ratios?
Well, they're all HWs, right?
Oh, yeah.
One's like this side over this side.
Yeah.
One and then this side
Like
over
it's
this
a
side.
total of 4, and then you have RW over HW, right? HW is 3, so you have RW over 3.
Well, 2 over 4 reduces to 1/2, and I multiply both sides by HW.
So what you write in the box?
RW equals 1/2 HW.
Why did you plug in?
Because that's specific to a time. That's at one specific time, the time we care about, but we can't plug that in until we've done the derivative. Until we have a rate equation, that time where the height is 3 doesn't matter. Gigi.
Oh, I just think.
Yes, you're right.
Now I get it.
Okay, now we'll do the derivative of both sides. Everybody feel okay with what I did there? Let's do the derivative.
Oh, yes.
CVW.
Yeah, dVW over dt. And we know that, right? That was 2. And here, let's reduce that. HW, we know, is 3. So I multiply both sides by 4 over 9 pi. And that's whatever, what are we doing, meters per second? Or you could make that a decimal if you wanted to. Huh? Again, I said strap on your big boy pants because this one was hard. And I'll tell you, the hardest part is this idea of like, oh, I don't have enough information to just differentiate that equation the way it's the volume equation as it's written. I have to come up with something else. And to be honest with you, coming up with that other idea, you're gonna need to probably be shown that other idea each time and then be able to remember to do it. Oh, on a cone problem, I should be looking for a similar triangle.
Yeah.
Oh, in this kind of problem, I should be thinking, I could use this idea or that, like it's not obvious to come up with it by yourself. It's very difficult. So for the most part, it's going to be, we'll talk about it. I'll show you the trick and you'll be like, I add that to my toolbox of like, in this type of an equation, I need to look for this kind of trick if I need to get rid of a variable so that I have enough information to do the problem.
Is this the hardest one?
I think I have 2 more in my example list here. I don't know that either one of these 2 necessarily are any harder, but they're all like at that same level, or I would say similar level.
You think one of these would be on the test? Not like Tuesday, but eventually.
Yeah, for sure. That one that you just saw is like a classic AP level related rates problem. We love cones. We love them. I don't know why. Actually, I do know why, because a cylinder radius is constant. If you're filling a cylindrical tank, the radius is constant. It's a much easier problem. If you're filling a cone-shaped tank, at every step, the radius is, changing. So what gets really fun is when you're filling and then emptying the tank at the same time.
Why? Again, what scenario are you ever doing that? Just decide.
At different, it's at different rates,
Yeah.
right? Like,
But
well,
why
this
are you
is,
filling it empty?
but this is a classic, this is a real world situation. Like if you're at the reservoir, you're pumping water into the reservoir from a well, and water is going out of the reservoir to people's houses at the same time. This happens all the time in the real world, where you have reservoirs for like industrial process that's running, whether it's like a city's water supply, like you have the big water tower, you're pumping water up into the tower, and the water's coming out of the tower and going into people's pipes to their house. All the time. All kinds of industrial processes, this is what it looks like. No. All right. So car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are heading for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 mile and car B is 0.4 mile from the intersection? So let's draw ourselves a picture. Here's my intersection. Actually, let's put it over here because we're traveling west. So like, right, that's west. Yeah, for intersection.
Oh.
So this is car B. There's car A. So we're traveling north, he's traveling west, right? I'm going to call this distance Y, right? Because it's changing it with respect to time. And we're calling this distance X, again, because that's changing with respect to time. Now, the rate in which X is changing should be called dx dt. And we know that that rate is, nope, that's the traveling west. Yeah, is traveling north, or west at 50, right? Except that's not quite right. What's wrong with this? Look at the direction. Negative. Yes, because we're moving to the left. That's tough to catch. A lot of time they'll say, give you some clue that it's negative or positive, but not this time. And then the rate in which y is changing. Yeah, dy dt, and that's going to be positive 60 because we're moving up. Because we're moving to the left. And then we'll call this distance between them r, and that's changing with time, right? That is not constant. As the cars get closer and closer together, that distance will be changing as well. So we'll call dr dt the rate at which those two cars are approaching each other. That's the variable that I'm looking for. Okay, what equation is going to relate the variables in this problem? Pythagorean theorem. And do we know x dx dt, y dy dt, and r?
Yes. Wait.
No.
What are we missing still?
We're missing
R. Can we get it though?
yes.
Yeah, pretty easy, right? Just Pythagorean theorem. So let's go do our derivative. So 2x dx dt plus 2y dy dt equals 2r dr dt. And we know r is going to be 0.5, right? I just did the Pythagorean theorem in my head because it's 3, 4, 5. So we fill in x is 0.4. Oh, no, wait a minute. This should have been A, right? Because car A was moving west and car B is going north. Whoopsie daisy. I was about ready to mix my two thingamajiggers and get all goobered up there. Already forgot to write the negative sign on that 50. So we're good, right? Here's the lovely part. What's 2 times 0.5? Just 1, right? So that just, we got what we want already by itself. So that's negative 30 plus 48. Is that it? No. 32? Okay. Oh my goodness, guys. No, well, yes, but it's not a huge mess up. All the algebra is correct. One of the numbers we wrote down was wrong.
Traveling north?
Here's why. What's happening to this distance between B and the intersection? It's decreasing. So what should the rate be? Negative.
There's no way this has to do with it too.
Right?
What?
What's happening to this distance as car A is, that distance is decreasing as car A gets closer to the intersection. So the rate should be negative. Yeah, it was not because we embedded it into the axis. It's because it's not dumb though.
I agree with you.
It's just math. I know. But the setup for this one was considerably easier than the cone, right?
Yeah.
Now, what was the hard part? Recognizing that both the derivatives were negative, right? The dx dt and dy dt both should be negative, which is not easy or obvious. Like I made the mistake when I did it because I just, north is positive because we're going up, and it's like, and it's like, oh, that's not right. Because I was going to get a positive answer for dr dt. And it's not, they're not getting further apart as they get closer to the intersection. So I knew something was up. Right? All right.
You did everything right on like the FRQ, just that part. I don't think
Well, most of the FRQs are multiple parts. So on a problem like this, if they asked you all of that together, that probably would be a 3-point question. And you probably would have gotten, like 1 point for doing this derivative correct, for doing like that correctly, like 1 point for pulling the value of r, and then like 1 point for your answer.
So 2 points.
So you probably would have gotten 2 out of 3. Would be my suspicion of like that's how they probably would have scored something like this.
Okay.
All right, last example here. A man walks along a straight path at a speed of 4 feet per second. A searchlight located on the ground 20 feet from the path is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? This is hard to envision what's going on. So here's the path. So this is the spot closest to the searchlight. The closest spot is going to be perpendicular, is a straight line, right? We're just going to straight perpendicular to the path. That's where the searchlight must be. This is where the man has ended up. Like the searchlight was on him here, and then as he walks along, it's continuing to follow him all the way to the end, right? So this thing is like turning and rotating like a spotlight. So the rate in which that's turning, what's called is that angle theta. So we're looking for d theta dt. Now we know that searchlight is 15 feet from the point of the path closest to the searchlight. So that side length is a constant 15 feet, right? Everybody agree with that? This side is the distance the man's walked from the starting position. That's changing with respect to time. I'm going to call that distance x. And we know the rate in which it's changing should be called dx dt. Is that distance from the start to where the man is increasing or decreasing with time? Increasing, right? We're getting further away from our starting spot, so the derivative should be positive. Sound good so far? Okay. What equation is going to represent the variables in our picture? No, because we have an angle measure.
Oh, that's a no, the side.
Which one? Talika? Tangent. Pierce, what's up?
Wait, how labeling the opposite why isn't it?
Oh, sorry, that is 20. Thank you. We misread the problem. X is 15 after we've taken the derivative.
Oh.
Not before, though, because that's at some specific point, right? X is changing with time. At time t, it's 15, and we're looking for the rate in which the thing is spinning at time t. Okay, so we can say tan theta equals opposite over adjacent. Everybody's okay here? Okay. So if we do the derivative, what's the derivative of tangent? Secant squared theta d theta dt, thank you. And what's the derivative of x over 20? No.
Oh.
What if we write this as 1 over 20 times x? Would that make it easier to see what to do? 1 over 20 dx dt. So I just need to then divide both sides by secant squared, which is the same as multiplying by cosine squared, right? Let's just write cosine squared here. So far, so good. How do I find cosine squared theta? Well, cosine is adjacent divided by hypotenuse, right? What's the length of the hypotenuse going to be when x is 15? 25. You could do the Pythagorean theorem to figure that out, or recognize that it's a multiple of a 3, 4, 5 triangle. We love 3, 4, 5 triangles, mostly to just make the algebra simpler. So cosine squared is going to be 20 over 25 squared. So far, so good. And now it's just a question of simplifying this down. Yes. Now, that's not the way I would have done it. Instead of doing tan theta of this, I would have done theta is tan inverse of x over 20. And the reason why I like doing it this way better is because I will not have to find cosine from the picture. So when I do that, that's now a chain rule derivative. I've traded in an easy derivative for a more complicated one. But I have everything I need. I don't have to go and do any trigonometry. That's the way I would have done it. Again, doesn't matter. Either way is fine. What do you guys think? So the homework there is listed. Notice I haven't bolded anything because, like, consider it all bolded. Yeah, we're going to do all of these problems will be a homework quiz problem at some point.
Oh, I got it.
So you really want to have them all done. You're taking the test on Tuesday.
Oh, yeah. For Thursday.
No, we have basic.
Asynchronous is Tuesday or is Thursday.
So
Or
next
next
month.
Well, we don't meet again in person until the following Monday.
Oh, okay.
So, like, you have basically over a week to do this, to work on these. And if you're stuck on stuff, don't worry too much about it. Okay? On the asynchronous day, on that Thursday, I have a set of MyEP questions related to this stuff that I'll assign so you can get some instant feedback, on stuff. I think I have like some multiple choice questions and like 2 free responders. I'll put those on Thursday. I'll put those into the OneNote also, although I'd like you to put your answers into the MyEP, even if you do your work in OneNote or whatever. Everybody's okay? Yes, certainly. All right. Yes, Pierce.
Are you pretty much like always trying to make a triangle?
Well, we had a sphere on the first one.
Yeah.
So it just kind of depends on the problem. Some of them we think about as cylinders. Some you might think about as a cone or a circle, or, you'll see a variety of stuff. Cones are pretty common, though. We like cones. And spheres, we like spheres too, for the same reason, because if you're filling a spherical tank, at every height, the radius is different, so you have two variables, as opposed to a cylinder where at every height, the radius is the same. Unless you have think about an oil slick as a very tiny cylinder, in which case as it's spreading out, the height is decreasing and the radius is increasing. You could do that kind of a problem, then a cylinder is fun because it's got two things changing with respect to time. And you're like, that sounds terrible.
Yeah.
I would say at this point, if you guys have any review questions for the upcoming test, if you have questions on stuff, we can do some of that right now. We still have 20 minutes or 25 minutes or something. If they've been working through some of the multiple choicers or some of the other stuff and you run into something you're stuck on, feel free to ask about this. I think, where was it? It was, there's one of these that was wrong. Chanel came and asked me about something this morning, and we found a mistake on one of my works. I think it was 15 or something. Let me look here real quick. It was this one, 16. And look at, this is no, it wasn't this one. Where was it? Let's look. It was one that was right. It was right. Yeah, it was 19.
Yeah.
Good. Yeah. So look at what I did. It just should have wrote that as ones. So that's supposed to be a 3. So that's supposed to be a -2. So that should be a -4. So this should be A, not D. So we found that one. My apologies here, folks. I goobered it with the most Mr. Kulik way possible, which is I did nothing wrong and she wrote the wrong number. Nobody has anything right away? You did? Okay. I was just going to stop the recording if nobody had one right away, but if you got something, we'll record it. I sure hope so. Because I did it at one point. Okay.
regular line.
I don't think I do. So Pierce, for number 48, this one right here. So it says, approximation. So I'm going to use a linear approximation to do this. So I'm just going to write the equation for a tangent line. So I have the 0.32 and the slope 5. And then I plug in 0 for y and solve for x. And that ought to do us. Remember again, a 0 is where the y coordinate is 0, where you're hitting the x-axis. So that's why I plug 0 in for y and then solve for x. Once I built my linear approximation, which is just a tangent line, right? Hi, Emma. It's a big yawn.
Grinding out.
It's that time of the season, right?
Yeah. Okay. So I've been like really confused doing the dy dx.
Okay.
I don't care which one I would do because I keep like I just don't know which ones to do for which.
Okay. So this, when I look at doing the derivative of this side, I see two functions being multiplied together.
Yes.
So I say, okay, that's a product rule. So that's like x times the derivative of sine x plus sine x times the derivative of x. Is that okay there?
Yeah.
And the derivative of x is
1.
1. So there's sine x.
Oh.
The derivative of sine x is
Cosine x.
cosine x. So that's x cosine x.
Oh.
That's it.
Okay.
Is that okay?
Yeah, this one. So confused because like the way you because I didn't even know what the answer was because it didn't even show up on the thing.
Oh, it didn't show up?
Yeah, it wasn't like circled.
Oh no. Let's look. Should I guess maybe your printout. Did you print it out?
Printout, yeah.
So
or no, actually on my computer it just didn't.
oh, that's weird.
I know.
Okay. So this is a chain rule, right?
Yes, it is.
So the derivative of the outside is arc cosine, and I think you've written down the wrong formula for that. So it should be negative 1 over x squared, or 1 over inside squareds, right?
So there's 2?
Mm-hmm.
Wait. Should I erase that?
No, because that's 1 over x squared, but our x squared is, our x is x squared, so we have x squared squared.
Okay.
The chain rule is the derivative of x.
So if we think about it this way, let's think about
You can erase
u
my
equals
stuff.
x squared.
Yeah, you can erase my stuff.
That's okay.
No.
So if I do that, if I do the derivative, I have 1 minus u squared times du dx, right?
Yeah.
The chain rule is the foundation.
So now let's plug our u back in.
X to the third is great. What do you add?
And then the derivative of x squared.
Which is 2x.
So,
That's 2x.
and then x squared squared
X
is
fourth.
x to the 4th. So
I just
that
get so
looks
confused with the
like
dy dx
that
stuff.
one.
Okay.
It just means the derivative.
Oh.
It just means do the derivative of this.
Oh, okay.
It's just another notation. So like f prime
is equal to
the same thing as dy dx, which is the same as like y prime. All means the same thing.
Okay, and then I just last question. I don't know how you got it to there. That was like I was confused.
So
on.
let's think about it the same way. Let's think of u as 5x. So the derivative of sine x, or sine inverse is 1 over 1 minus.
Square root of 1 minus x.
Well, we're going to use a u, right?
Right.
And then du dx. And then we plug our u back in. And 5x squared is 5 squared is 25, x squared is 5, and the derivative of 5x is just 5. So there's
Okay, and the x squared, is that just from the outside that you did? Or, oh, okay.
right. It's
But
just
you
the
kept it though. Oh, it's just the
well,
formula.
5x squared
Right, which is
is 5x times 5x,
Which is 25.
25x squared, right?
Hmm. Oh,
Right.
duh. Oh, that's why I probably got so confused.
It's okay. Sometimes you just have to write it, like if I write it all out,
See,
it's like,
look, I literally have like all the dy dx like circles because I know this one especially because like I know you have to put it to
this
the
is
other
an
side.
implicit differentiation problem.
Yeah.
So that looks fine. Now this is a product property, right?
Yeah, because it's 2y and then the y is dy dx.
So you have 2, and then so you have x times the derivative of y plus y times the derivative of x, and then 2y dy dx equals 0. So the derivative of y is
Y.
just dy dx, right?
Yeah.
So there's my 2x dy dx, and derivative of x is 1, so I have 2y,
Yeah.
and that's,
Wait, because the 2y from here.
so I have the 2 distributes,
Okay.
and I have just y times 1, so just 2y.
Why 2y?
I know.
Oh.
I think that you wrote it in a weird order for me.
I probably switched them.
Yeah,
Okay.
is what it looked like, but I was not expecting that. I wasn't
My
even
bad.
looking that far. That's okay. So that's there, right?
Yeah.
Now we just are going to take everything without a dy dx and put it to the other side. So we subtract the 6x and then minus 2y.
But I'm just confused why it was in like a fraction. Is that you
Because then
just-
we're going to divide.
those two? Oh, okay. Is that what you usually do?
Well, it's because we want to get, basically what we did is
You want the y.
we factored that off.
Okay.
So then we'll divide this stuff over to get the dy dx by itself.
Okay, so that would be so the things without the y's would be 6.
Subtract it over,
Oh, you
subtract it over,
subtract it over, so both are going to be negative. And then
because
you
we just have a
divide.
0 over there, right?
Got it. And then you divide those two technically over. Ah, okay. This one, I don't know why it looks like that. I was so confused. But in my final answer, I got like 6
Oh,
cosine.
this just like, I don't know, somebody who did this did like, made their answer this thing. It looked good when I picked the question, like when I look at it in the MyAP, it worked.
Right.
And then when I printed or converted to a
But I
PDF,
don't
it
know,
just
is
went.
that the correct answer?
bananas
or
there.
Is it only.
It should be that.
Because I ended up with F.
So we do the derivative of the outside, right?
Right, I did that.
And then the inside stays the same.
Yep, I did
And
that.
then we have times the derivative of the outside,
Which is F.
right?
Yeah.
So the derivative of f
It's F prime. 2x.
of x
Or
squared
x squared. And
times the
then
derivative of
x squared, which is 2x.
so we have
Or a little
we
chain
have
rule.
that guy times that guy times 2x.
I have it.
Okay. So it should be
Oh, so it's the ones after that are gonna be like.
Those are the only.
right, but that's
But it's when F.
oh in 3. Okay. So plug 3 in, that's a 6,
Yes.
right? That's a 9,
Yeah.
and that's a 9.
Yeah. That's why I got f prime of 9. Or yeah, f prime of 9, f of 9.
Right, but you also need a f prime of 9. Right.
So I
Which
still had it, but
Yeah, I think which is this one here, right? 6, and then there's f prime of 9 cosine of f of 9.
something like that. But I
Yeah.
still technically had it though, right?
That's not the right answer.
Well, no,
But,
but that
yeah.
was my final.
Oh
answer,
yeah, yeah,
'cause I
yeah. Oh,
couldn't
oh yeah. I
find
didn't
it.
see that. I didn't see that right there. Yes,
Yeah,
that's
'cause
correct.
I couldn't find it, so I was just like, is
Yeah.
it 6 cosine of it? Sorry, I have a lot of questions.
That's okay.
I've been doing them, and I'm just circling the ones I don't.